Okay, we're back and we're looking at our example. So here's the example we were trying. We have a triangular plate, uniform density. We're going to try to find the center of mass for it. And the function for the edge of the plate is y1 of x equals minus a over bx plus a, the intercept. Okay, so we're going to take our formula for the coordinate in the x direction, the x coordinate of the center of mass. I'm just going to write the total mass over here. Sometimes people do it that way instead of saying 1 over total mass times this integral. We'll just say m x coordinate. And the integral should be rho x dA. I've already pulled my rho out because I'm assuming it's constant, uniform across the plate. All right, so we've got the integral of the x position and the dA. And then the dA, I'm going to look up at my figure, and I've sketched in. I'm going to again do these vertical strips. That's my area element. That whole strip has the single value x, so I know it's the right shape to be using. And so I can just write down what that dA is. It's this end minus this end, so technically it's y1 of x minus 0. We don't really need that in there, but I put it in there. And then it's got a width dx. So this is the integral we have to do. The integral in the x direction, from 0 to b, of a functions of x, right? Y of x times x, so we can do that. So we'll put that in there. We've got our y1 of x minus a over b x plus a times x, integrating with respect to x from 0 to b. I'll just multiply my x in, so x squared and x. Do the integral, so the x squared term turns into an x cubed term divided by 3, evaluated between 0 and b. The x term gets integrated to an x squared over 2, evaluated from 0 to b. If we evaluate the endpoints, the zeros are going to go away, of course, so I'm going to get minus a over b, b cubed over 3, and a b squared over 2, all times rho, the density. And if I cancel out these b's here, I notice that both terms are a b squared, so 1/3 and 1/2. The common denominator is 6, so it's 3/6 and 2/6, which gives me a net result of 1/6. So the result of the total mass times the x coordinate of the center of mass is 1/6 rho a b squared. So now I better go and calculate what that total mass is, and that's just going to be the integral of dm over the whole shape, or rho dA. Again, pull the rho out because we've assumed it's constant. And so then dA, I'm going to do the same thing, just do these vertical strips and integrate it over the whole shape. So I know what that vertical strip dA is. It's the height minus a over bx plus a, so y1 of x, and then a width of dx. So this is the integral I have to do. It turns into an x squared term and an x term evaluated from 0 to b. And so I get this, minus a over b, b squared over 2, plus ab. The b's are going to cancel here, leaving me just minus 1/2 ab plus ab, so the whole result is rho ab over 2. So now I can put these two results together and calculate my x coordinate as 1/6 rho ab squared divided by 1/2 rho ab. The rho's are going to cancel, the a's are going to cancel, one of the b's is going to get canceled, and I'm going to be left with 2/6 b, or 1/3 b, which is good. Check the dimensions of that. Dimensions of b is the length, and that's what I ought to get for the coordinate of the center of mass. All right, how about in the y direction? Right, so we also want to calculate the y direction. So y center of mass coordinate. I have to do that, note that symbolically so it looks different from my other y's. And so we need to do the integral of rho y dA. And so let's think for a second of what that dA needs to be. From A to B, so we have this shape here, and we said that this boundary, this function, was y1 of x equals minus a over bx plus a. And so to do the y-coordinate, we really need to have horizontal strips like this, so that that whole chunk of mass has the same value of y, so we can add this up properly. So our dAs are really going to be this horizontal strip here. So let's just write that down. We're going to have the integral of rho y. And so the width of this strip is just the x value here, right? So it's x1 of y. again minus 0, so that's the width of the strip, and the height of that strip is dy. And we can check we're doing the right thing because we're integrating with respect to y, and this is a function of y, as is this, right? So that's good. We know we can do, that's a thing we can integrate. So we're going to need x1 of y, which means we need to invert this equation for x. So I need to solve for x up here. So x is going to be, y1 minus a, right? So y1 minus a, and then times minus b over a, right? Inverting that term. So that would be my function x1 of y. So let's put that in here, over here. So then pull the row out because it's constant. So I'm going to integrate y times this, minus b over a, y minus a, dy. And then dy, what am I integrating from? I'm integrating strips from here up to here, from here to a, from 0 to a, the limits. Right? So notice these are y limits because we're doing integral with respect to y. Alright, so that's going to be the integral. Let's distribute this y in. We're going to have minus b over a y squared minus a y plus, let's see, what did I do here? Oh, that was dumb. Right. I need to distribute this term into this, so that's not correct. Right? B over a times y. The a is going to cancel. I'll be left with a b, and the negatives are going to cancel as well. So this whole term was just completely wrong. It's plus b y. All right. And all of that is being integrated with respect to y. So if I do that integral, I'm going to get y cubed over 3. It's still minus b over a. The row is still being multiplied. And then plus by squared over 2. Whole thing evaluated between 0 and a. And so then that works out to be rho b a squared over 6. I'll let you check that on your own. See, that works pretty well. Okay, so then our y-coordinate of the center of mass should be this term, rho b a squared over 6, divided by the total mass, and we know that that was rho ab over 2. So the rho's are going to go out, and the b's are going to go out, and one of the a's is going to go out, and we're going to get a over 3. Oh, interesting. That's an interesting result. You can check. Again, dimensions of length, so that's a good thing. And you can go and actually look up what is the center of mass of a triangle, and you'll find out that they are 1/3 of the base under consideration. So that's why that's the right answer. Okay, so hopefully that gives you a sense of how to do these center of mass integrals for various shapes.